Okay, hello again. This is for lab number 4, eng2151. Today we're going to look at rectifiers, but we're going to have to deal with a couple other things too. So I'll start with the circuit. Okay, so normally when I have a class in here, we talk about the different components and I try to get them to guess what things are. You wouldn't believe what some of the things come up as. So I'm just going to tell you what these things are, right? This is a plug-in, right? This is going to plug into your receptacle. So coming out of your receptacle, right? You have a sinusoidal voltage, right? It's 120 volts, 60 hertz. But that is a certain measure, right? And you're taking those things in class, right? So 120 volts is 120 volts RMS. So what that really means though, it's about 170 volts peak, 340 volts peak to peak. Okay, does that make it a little more scary? Well, I don't know, you might have been zapped with 120 before. And it's not that bad, but then again, depending on the conditions, it can be bad too, right? Because it's the current that kills you, not the voltage, right? So anyway, so this is what we're getting out of our outlet, okay? And here we go, we're feeding that signal into, this is our transformer. Okay, and what a transformer does is it'll take an AC voltage. It doesn't work with DC, right? It takes an AC voltage and steps it down to a lower voltage. Now it can increase it as well, but primarily it's used for taking large voltages and shrinking them down to a lower voltage. Okay, and I believe in our case this is 12.6 volts RMS on what we call the secondary, okay? So what the transformer is it's two coils of wire, your primary and your secondary. And your primary gets energized by the 120 volts RMS, okay? And when it flows through the coils of wire, it creates an expanding and contracting magnetic force based on the AC current flow. And what it does is it induces a voltage into the secondary coil at a certain ratio. And it's based on the number of turns on either one, right? So, and that's what we call the turns ratio. So depending on the number of turns of the primary versus the secondary, that controls how much the voltage is going to be either expanded or shrunk down, okay? So for that, that's what we have here. So we get 120 volts in and 12.6 volts out. So the turns ratio on the transformer is about 10 to 1. Okay? And then the whole point of this lab is dealing with rectifiers. Okay? So now this is our rectifier. It can also be called a diode. And simply what it does, it only allows current to flow in one direction. Okay? So in this case, it allows current to flow basically in the direction that the arrow points. So on the positive cycle, the current is going to flow through the device and come through the resistor. So when we look at on our oscilloscope, right, on the positive cycle, it's going to allow that current to flow through and have the voltage appear across the resistor. But on the negative cycle, when the current's trying to go this way, it blocks the current. So the current flow is 0, which means there's 0 volts gets induced in here, right? And then it comes here again, right? So essentially this piece here just gets chopped off, okay? So we're left with basically half the cycle And that's why we call this a half-wave rectified circuit. Okay, so it's halfway rectified. Now the other thing that we're trying to get to with this, right? So in the previous labs, and of course if you were in the lab, you'd actually be using this equipment. In the previous lab, we're using DC power supplies, right? And essentially this is what we're doing here. We're creating a DC supply. So DC means direct current, and it means that it's always flowing in one direction. So here's the thing. Our DC supplies that we use in the lab, they're nice flat DC voltage, okay? Now here, we don't really have a nice flat DC voltage, okay? This is actually called pulsating DC, okay? Not exactly ideal, but it is still a DC current because the current's only flowing in the one direction, okay? Now say for example, if we wanted to take it another step and to try to work, to get towards creating a nice flat DC. Gee, now we need to have a device that will charge up and hold the voltage charge. Gee, I wonder what that is. Well, we just were dealing with that before, and that's your capacitor, right? Because the capacitor charges up and tries to maintain that voltage. So what we do, we put a capacitor across the resistor, and that charges up and it tries to hold the voltage at a steady state. Okay, and what it's going to look like here is going to come up like this, and then it's going to somewhat discharge, right? Because it doesn't, the capacitor isn't perfect, it doesn't hold the charge ideally, right? So there's a bit of discharge, and then it charges up again here, and then it discharges again. Okay? So now this is what we call, so now you're not going to see this underneath here. And again, I'm going to do the demonstration here, and I'm going to show you, right? Where this part here no longer exists, you just get this rippling voltage, right? And we call that the ripple voltage. And that's what we got. So again, it's not the nice super flat, but it's pretty flat, right? So when I show you, you know, it's pretty flat. And then the only thing we'd be missing is a voltage regulator. We're not going to deal with that in that lab. The regulator device is a little more complicated, right? So we're not going to deal with that. But if you wanted to make an okay DC supply, you could just throw this into, well, if you bought like a wall wart, right? The little power supply you plug into the wall, and then it comes out like, say, for a phone charger or something like that. This is what's in there, right? You have your transformer, you have your diode, and you have a capacitor. And that's what you have. There's no voltage regulator, right? Because as long as this voltage is higher than your battery voltage, it's going to charge your battery, okay? So that's what we're going to see in the demonstration here, okay? So now for the second circuit, again, it changes a little bit here. Okay, so now if this configuration looks a little similar to something we've done already, it is, right? This is called a bridge rectifier, right? We had the Wheatstone bridge where we had the 4 resistors in lab 1, right? Well, this is the same, similar configuration, but using diodes, okay? And then we have our load resistance in the middle, okay? So what we're going to see here, and I'll draw out the current flows, okay? So on the positive cycle, right? So the positive cycle is coming this way. It's going to come through this diode, through here, and back to here. Okay? So it comes here, here, here. So the current flow is flowing through the resistor this way. Okay? In the negative cycle, the negative's coming this way. It's going to allow the current to go this way, and then back this way. Okay, so it comes like this. It uses the other two diodes. But the thing that you really want to see here is that look at the direction of current through the resistor. They're both in the same direction. So what we've done here so I'm getting ahead of myself. What we've done here is we've taken the negative cycle and flipped it up. So now we're using the full wave. So this is full wave rectified. Okay? And so this is a little bit nicer circuit. Okay, because what ends up happening now, these are coming along at 120 times a second, 120 hertz. The other would be 60 hertz. And so what you have now is when you get this ripple and we put our capacitor across here, because we're going to do that same thing for both circuits, this ripple is smaller. So this is a better circuit. So when you have your phone chargers and say you have your nice Apple and you paid like a gazillion dollars for it and you figure, oh, well, it's going to have the best circuitry. Now, actually, I shouldn't actually say that because some phone chargers have a little more circuitry in it than just this. But if you get your cheapy generic chargers, they don't have that. You're paying for 3 more diodes, and that's money to a company, right? So you get the cheapy, crappy one, right? Because you guess you get what you pay for. Okay? So anyway, this is what we end up with. We have a lower ripple voltage, okay? And so for our demonstration, we're going to have to make up this chart here, and what I'll do is I'll move this over here. Okay, so what the chart is going to look like, it's going to look like this. It's going to say half wave without capacitor, half wave with capacitor. Okay, full wave without capacitor, full wave with capacitor. Okay, and then we're going to measure a couple different quantities here. We're going to measure V peak. Okay, we're going to measure VRMS. Okay, we're going to measure VDC, and we're going to measure V ripple. Okay, so just to kind of clarify, and I'll show you this in the demonstration, RMS is the average of the sinusoidal waveform, okay? But DC is the average of the waveform too, right? Well, here's the difference. So what we're going to have, when we have our ripple voltage, it's going to look like this, right? Well, or something like that, right? When you measure the RMS average value, it's the average of the rippling voltage, the actual moving AC portion of the, well, I can't really call it AC because this is DC now, right? And it's just going to measure the average of this portion of the waveform, where VDC is going to measure from the ground to the average value of the waveform. So it's two different quantities, even though they're both kind of doing an average, but they're taking two different averages, okay? Okay, so this is the chart we're going to make up. And then as I go through, I'm going to make all these readings for you, and we will, and you can fill in your table, okay? Now the other part of the lab, we look at voltage regulation, okay? And probably again, if we were working in the lab, I probably would have talked about this a little bit, but simply it's this. if we have, say, a 12-volt supply, and let's say this is a 10-ohm resistor, okay? When we measure, and we've got nothing else in the circuit here, right? When we measure here, we should measure 12 volts. But we don't, okay? Because here's the problem. Inside this power supply, it's not ideal. Again, none of these things are ideal. Like just with our resistors, it's plus or minus 5%. Nothing's ideal, okay? So inside of here, there's a small resistance, R internal. So this is our whole power supply here. So let's say R internal is 1 volt, okay? And let's make it easy on me here. Let's make this 10 volts, okay? So we think we're going to measure 10 volts here, but what happens, right, is we have, well, okay, let's make this 11 volts. So what we have here, so we have 11 ohms and 11 volts, so it's going to have 1 amp. So there's going to be 1 volt here. So we're going to measure 10 volts over there. Okay? Now let's say this resistance here, and again, we're going to deal with some pretty high currents here. Let's say this is only 1 ohm. Well, if this is 1 ohm and this is 1 ohm, now you're only going to measure half of the voltage here. So you're only going to be measuring 5.5 volts. Okay? And we call that the loading effect of the circuit. It's loading down the power supply where you're drawing so much current out of the supply, a lot of the voltage is getting dropped inside the power supply and not making it through here. Okay? So, what we're going to do, and we're going to use one of the circuits from our part A of the lab, okay? And it doesn't matter which one, because the same thing's going to happen. Okay, and we're going to make this chart. Okay, we're going to have R and we're going to have V, right? So we're going to start, let's see, what's the, I will tell you this, the resistances that we're using in the lab when we do the demonstration. Okay, I'm just trying to think what they are. I think it's 510. 270, 220, 110, 55, and then I can also put two 55s in parallel. So you put two 55s in parallel, that's 27 and a half. Okay? And so as the resistances get smaller, the voltages should go down. Okay, actually I can do an open circuit one as well. So infinite resistance, right? So an open circuit test, we can figure out what the voltage is for there. And then as we add resistance, okay. And now here's the other thing I always like to kind of bug the class about. So when we get smaller resistances, we're actually making the load bigger, right? Because the load is determined by the amount of current draw. Right? And we know from our other labs that the lower the resistance, the higher the current gets. That's the bigger load. So 27.5 ohms is a much larger load than 510 ohms. All right? So that's what we're going to do then. We're going to go through these different quantities. We're going to do this, and then you're going to make a graph for your voltage regulation. All right? Okay, so that's it for the instructional part. We'll move over to the lab and we'll do our demonstration, okay? Okay, so here we are, lab number 4, rectifiers. Things are a little cluttered here. So we're going to be using a voltmeter that's off the screen, but I'll tell you all of the different values that you're going to need for your table. We can see the oscilloscope. I'm hoping you can see all this stuff. Here over here is our transformer, right? You can see that it's kind of got this ferrite core and the coils of wire go around these things. There's 3 terminals here because it's a center trap transformer. And So basically from the center to one side is going to be half of the voltage, and then from the full voltage is from side to side. Okay, and this is just like your transformer out on the pole, that, you know, the hydro pole outside your house that feeds your house, right? Because what comes into your house is 240 volts. But from one side to the other is 120, one side to the other is 120, right? And then inside of your breaker panel, you have a bus bar that goes like this, and one's one side, one's the other, and then the neutral comes down the center, and then this says, oh, this is 120, and then this is the opposite 120. So if you have a 240 volt breaker, it goes across these two connections, but if it's a 120, it just goes from here to the neutral, right? So from here to here, or from there to there, right? Okay, and then if we come over here, here's our diodes, and I'm not sure whether you can see those, but basically they kind of look like the resistor, except they're just pure black, there's no color on it. But there is one silver stripe on the one side, and that corresponds to the stripe on the diode, which indicates, like, that's actually called the cathode, right? The anode would be the other one. Okay, so I've got the two different circuits here. Right now I've got the half-wave rectifier. So you can see right now I've got my input waveform, there's my sine wave, and I'm using just half of it because I am using just the lower voltage. But then you can see, right, that the negative part, and I've got this a little offset so you can just see it better. The negative part is offset a little bit, but the negative part, sorry, is clipped off. And then the positive cycle is allowed to come through, right? This is our half-wave rectified circuit. So this transformer puts out 12.6 volts center tapped, okay? So that would be your RMS value of that, okay? So the peak to peak would be 24 plus, you know, it's going to be 30 something volts, okay? I'm not going to be able to calculate that off the top of my head, okay? And so actually, well, what I've got here, I can't see it, well, it's 21 volts peak to peak for half the, so it's probably going to be 42.6 volts total output, okay? And then we're coming to our one diode, and then we're going to our load resistors over here. Now we've got these other load resistors, and I'm going to try and show these to you because we're using higher wattage resistors, right? So because we're going to deal with more current. So you can see again, like the resistors don't look the same. These ones kind of look the same, but these get a lot larger because we're going to pass more current through them, and so they have to be able to handle that much more power, right? And basically what I said before, the more power you're using, the bigger the components, okay? Okay, so we're going to make some readings right now then to go for the half wave rectified. Right now we're doing it without the capacitor, right? And so the values, right? So you have your table from the introduction part, right? So half wave without the capacitor. The peak voltage is 10.1 volts. The VRMS is 3.76 volts. The VDC is 2.98 volts. And then the V ripple, and I don't even call this, I call it ripple when I've got the capacitor in the circuit. This, well, they still call it ripple voltage, but I mean, that's pretty significant ripple. And the ripple voltage is the 10.1 volts. Okay, so now I'm going to put the capacitor in, and all I have to do is just clip it in under here. Okay, so you can see now that the capacitor is charged, and see how much ripple there is there? I mean, it's actually pretty flat, you know. So even, like I say, we had to build a DC power supply, you need the diode, the capacitor, and then you need the voltage regulator. So here we are, we don't even have the voltage regulator. We're not even using the better circuitry and yet we still have a pretty flat voltage. Okay, so now the peak voltage, again, is going to be 10.1 volts. The VRMS, and again, now the RMS is taking the average just of the ripple, and that's 0.19 volts. Okay, the VDC is 9.4 volts because now it's the average of right from the ground up to the ripple voltage. And the ripple voltage is 1 volt. Okay, so those were the readings for the half wave with capacitor. Okay, right, so now we have our full wave rectified circuit hooked up. And you can see now that it's traveling now at 120 hertz. Our peak voltage is 9.2 volts. Okay, and that's something I never mentioned before at with the half wave, we had 10.1 volts. Now we're at 9.2. And the reason why it's dropped is that these diodes will drop 0.7 volts each. So from the peak input, we lose 0.7 volts on the half wave. But now we're going through 2 diodes in each direction. So we lose 1.4 volts. And so that's why the voltage peak is different. All right. So now, our peak voltage is 9.2. Our VRMS is 3.15. Our VDC is 5.3. And our V ripple is 9.2 again. All right. So now I'll put the capacitor on. Okay, and now it looks like almost a totally flat line. Our peak voltage is still 9.2 volts. Our VRMS is going to be something really small, 0.08 volts. Our VDC is 8.7 volts. And our ripple voltage is flickering, well, it's 0.5 volts. Okay, so again, so the ripple voltage is half of what it was with the quarter because it has less time for that capacitor to discharge. All right, so now what I'm going to do is we're going to go through the voltage regulation part of the lab. Okay, so it doesn't really matter which circuit we use to do the voltage regulation test because the same things are going to happen. So we're going to do, because we've got the full wave hooked up right now, we'll use the full wave without capacitor, right? So right now, okay, so if I open circuit this, so our first measurement, so right with infinite resistance, right, open circuit, is 5.94 volts. At 510 volts, or 510 ohms, sorry, 5.3, 270 ohms, 5.24, 220 ohms, this isn't going to make too much of a difference, 5.22, and then we can do 110 ohms, 5.15, 55 ohms, 5.08, and if I had one more lead here, oh I do, I have one more lead right now, and we'll do 27.5 ohms, is 4.9, so 5 volts even. All right, so those are the measurements for your voltage regulation. And that concludes lab number 4. All right, so 2 weeks and I'll expect a report. Or get it in as soon as you can, especially like the next lab. I don't know how much time will be left in the semester. Just get it in as soon as you can. You should be writing this stuff up right away because that's the best time to do it. All right, okay, thanks, and I'll see you for lab number 5.